Hello everyone. Here are some special lectures in time domain analysis of the dynamic circuits in the PEC course. We will discuss the unit step function and the unit step response, the unit impulse function, the unit impulse response, and the convolution integral. They can be ended after the time domain analysis of first order dynamic circuits or the time domain analysis of the second order dynamic circuits. Firstly, we will discuss the reason for A1 to A4. Let's take an abstract example. Suppose this circuit has only one excitation, a voltage source, and suppose it's ET, in which E means excitation. This network is a complicated dynamic circuit containing resistors, capacitors, and inductors, and many dependent sources. In the previous discussion on the time domain analysis of the first order or the second order dynamic circuits, this is often a direct current excitation. In this condition, the capacitor is open circuit and the inductor is short circuit in the steady state. But in electrical engineering, the possible excitation includes not only DC excitation, but sine excitation as well, which will be discussed in the sinusoidal steady state analysis of the dynamic circuits in detail. Specifically, after learning lecture 64, you will clearly know the steady-state solution of the dynamic circuits with sinusoidal excitations. It's not difficult to learn. Besides, there are many other conditions. For example, the excitation is a periodical, non-sinusoidal one. With this excitation, the difficulty of the time domain analysis of the dynamic circuits is a steady-state solution. We will discuss the steady-state analysis of the circuits with periodical excitations in lecture 90. Besides, there are many other conditions in fact. For example, one excitation has such a form. It starts at t equals 2 seconds and ends at t equals 3 seconds. Its expression is e to the power of t minus 1. With such an excitation, we can hardly solve the time domain analysis of the dynamic circuits by the methods we've learned before. After learning A1 to A4, you will grasp a convolution integral which will help you to solve the time domain analysis of the dynamic circuits with such a special excitation. You may think this excitation is made up deliberately for special reason and is not persuasive. In fact, we can take a real example. The speaking voice of mine is an excitation to the microphone and the sound processing circuit. So, what's the response of one capacitor's voltage in the sound processing unit? For such a non-periodical and irregular sound signal, what's the corresponding response? Similarly, we can also use the convolution integral to find it. After learning and grasping the whole contents of A1 to A4, you will be confident in dealing with the time domain analysis of dynamic circuits with any excitation. Well, let's start from the easy contents. Firstly, we will need to introduce the definition of the unit step function. The unit step function is called epsilon t. The unit step function is a discontinuous function. When t is less than 0, it equals 0. When t is greater than 0, it equals 1. The graph of the function is like this. We can give a physical explanation of the unit step function. Look at this graph. When t equals 0, the function seems like taking a step up, so it's called the step function. The height of the step is 1, so it's called the unit step function. You may be confused about what equals epsilon t equals at t equals 0. This definition expression doesn't answer this question. There are different definitions in different textbooks, and we won't discuss it in detail anymore. We need to point out that we are often interested in the value when t is greater than 0 plus. So we just need to know when t is greater than 0 plus epsilon t equals 1. So there's no question for solving circuits. With the concept of epsilon t, there is a hidden advantage. The expression of switching circuit will become easier. We will take 2 examples. In this graph, N is a dynamic circuit with RLC and dependent sources. Before switching, the whole circuit is connected to the ground. In other words, the energy of all energy storage elements is exhausted. The circuit is in zero state condition. At t equals 0, the switch is turned on, and the independent voltage source supplies the energy to the circuit. This is a switch process controlled by a single pole double-throw SPDT switch. With the definition of epsilon t, the whole switch seen from here to the left and the source can be equivalent to a voltage source. What's the value of the voltage source? Please think about it.